Let's talk about the different types of machine learning models for clustering and how you can know exactly which one to choose. Clustering is when you give your machine learning model a bunch of unlabeled data and ask it to discover natural groups based only on the similarity of points. There are tons of different clustering methods out there, but the right one depends on what you're actually trying to do. So to pick a model, start by naming the problem you're solving. If your goal is to cluster fairly quickly and you already have a rough idea of how many groups there should be, then you'll want to use k-means clustering. Imagine that you drop k number of magnets on a table full of iron fillings. Obviously, each filling will slide towards the magnet closest to it, and all the magnets will shift and slide a bit towards the fillings attached to them. K-means clustering does this exactly over and over again, but with a real dataset. Essentially, you choose how many clusters you're going to have and place them randomly on your coordinate grid full of data points. Then you assign each point to its nearest center and move the center to the average of all the points in its group. We repeat this over and over and over again until the centers don't shift a lot each time we repeat the process. This works best when your data is a few blobs on the coordinate grid, kind of round and separated from the others. And it's sort of the default clustering method that we usually go with when we want something quick and fast that gives us a reasonable first draft. Now, if your goal is to use k-means but avoid potentially getting some bad clusters just because you had unlucky random starting points, then you'll want to check out k-means++. Regular k-means always picks the centers blindly, kind of just hoping they work out. But k-means++ is more careful. It tries to spread the initial centers out so that they're not all clumped in one region. This means the algorithm will usually converge to better, more meaningful clusters instead of some random lopsided ones. And from your point of view as the coder, this feels exactly like the k-means pipeline, but with more clarity. Now, if you want to find clusters of any shape and also call out random noise, then you'll want to use dbScan. Instead of drawing circles around centers, dbScan looks for crowds of points, places where a lot of points are packed closely together. If a point has enough nearby neighbors, it's part of something we call a dense region. Those dense regions grow into clusters, and any point that doesn't fall into a dense region is classified as noise. It's kind of like saying these three groups of people are clearly part of the crowd, but that one person standing alone in the hallway is not part of any group. This is often great for real-world scenarios where your data is often messy and curved, and when you don't want to force every single point into a cluster. But if your goal is for your model to notice really subtle structures and curved shapes in your data, then you'll want to use spectral clustering. At a high level, this method does not think in terms of raw coordinates, but instead thinks in terms of who is similar to whom. It builds a sort of web of connections between similar points and looks for parts of the web that are tightly connected within itself and only weakly connected to the rest of the parts. Mathematically, it does this by turning that web into a matrix, transforming the data into a clean space whose connection patterns become cleanly separated, and then running a simple clustering algorithm there. That's why it works so well when clusters bend, wrap around each other, or are separated by more connectivity than just a straight line distance. Now, if your goal is to cluster data that is naturally represented as a network of connections, you'll want to check out Markov clustering. Here, the core idea is to really try to mess up the connections in that graph by spreading it and concentrating it to reveal which parts will stay closely grouped together. Imagine your data as a network of nodes with connections between them. The algorithm repeatedly spreads probability mass along these connections so it can move through the network and sharpens the value so that the strong roots get stronger and the weaker ones get weaker. Once you've repeated this process many times, the flow of the movement tends to stay trapped inside tightly connected groups of nodes and almost never crosses into other parts of the graph. And those regions where the movement and the flow keeps circulating around are what the algorithm calls clusters. Now, if your goal is to obtain soft, probabilistic, flexible clusters instead of hard assignments, you'll want to try out the Gaussian mixture models. Conceptually, you assume your data is representing several smooth blobs in space, each blob representing one cluster with its own distribution and spread. The algorithm alternates between two intuitive steps. Then it adjusts the blob's positions and shapes based on those estimated memberships. Repeating this makes the data settle into a configuration that explains the data well and gives you for every point a probability distribution over clusters instead of a single yes or no label. And lastly, if you're working with very high-dimensional, complex data such as images or audio where the raw inputs are too messy to be fed into the model, you'll want to check out Deep Cluster. The main idea here is to first let a neural network learn a compressed representation of your data so that the important patterns are captured. And they're captured in something called a lower dimensional feature vector. The model then chooses to cluster the feature vectors instead of the raw data, and you treat those resulting cluster labels as temporary targets to further train the model. This loop of learning the features, clustering them, and using those features to refine the model gradually shapes a feature space where similar content ends up close together. In the end, you get both a useful representation and meaningful clusters even though you never had human-provided labels. And those are the top 7 clustering methods in machine learning for you. So if you learned something from this video, then don't forget to save it for the next time you're clustering your data and follow for more.